So combustion analysis. This is a common technique for figuring out the empirical mass of compounds. It's especially useful for organic compounds, those containing only carbon, hydrogen, and oxygen. If we know the mass of the products that are formed and the composition of the constituent element in each of those products, we can figure out the mass of carbon, hydrogen, and oxygen that were in the original formula, in the original compound, and then we can use the calculation that we've already learned to calculate the empirical formula. When you burn organic compounds with plenty of oxygen, all of the carbon is going to form carbon dioxide. All of the hydrogen in that compound is going to form water. And then the original mass of oxygen, if there was any, we have to find by subtraction. So this is what an apparatus for combustion analysis might look like. The sample is weighed and put into a furnace with a stream of oxygen. So the sample burns, and the combustion products, which are water and CO2, pass out of the chamber because the oxygen is flowing in, and they go through a tube containing a water absorber that will absorb all the water that's formed, and then through another tube containing a substance that will absorb CO2. So these tubes are weighed before and after, and the difference in mass of this tube is equal to the mass of water produced by burning that substance. The difference in the mass of this tube is the mass of the carbon dioxide produced. Any questions about that? So let's do an example. Upon combustion, a compound containing only carbon and hydrogen produced 1.60 grams of CO2 and 0.819 grams of water. Find the empirical formula of the compound. So we know that there are two elements, carbon and hydrogen, but they're giving masses of these two compounds. So the mass of CO2, that contains the carbon that was in the original compound, plus oxygen that combined with it in the process of burning. So what we need to do is take this mass of carbon and figure out how much, the mass of CO2 and figure out how much carbon is in there. So there's different ways to do this. I'm just going to do the one that pops into my head first. So 1.60 grams of CO2. Remember, what we did with the empirical formula is we took the mass of the element and converted it to moles of the element, and then we did the ratios of the different moles, right? So here we've got a mass of carbon dioxide. Could we figure out how many moles of carbon dioxide we have? Yeah, and from that we can figure out how many moles of carbon we have. So first we're going to convert this to moles of CO2. So we'll divide by grams of CO2. Left my calculator in the office. Cell phone to the rescue. 12.01 plus 2 times 16. So the mass there is 44.01 grams. And that converts to moles of CO2, but we need moles of carbon. How many moles of carbon are in 1 mole of CO2? 1. We get that from the chemical formula. C, understood 1, O2. So there's 2 moles of oxygen and 1 mole of carbon in each mole of CO2. And sometimes that one is so simple that we overlook it because it can't be that easy. Well, occasionally there are things that are that easy, and it almost seems like they are easy to trick us, right? Yeah. So 1 mole of carbon to 1 mole of CO2. And sometimes students ask, why do I have to write that down? Because you got to show how it happened, right? And sometimes it's not one-to-one. And so it's important to just write it down so that you don't accidentally overlook something. So we can do the math there, 1.6 divided by 44.01. And my starting number had 3 significant figures, and so I want to keep a minimum of 3 significant figures here. That would be the 363. And I'm going to keep 2 extra digits, because that's what I do. Avoid rounding errors. So there's my moles of carbon in the original compound. Now I need to do a similar calculation with water. So I've got 0.819 grams of H2O. So I'm going to convert that to moles of water. I need to divide by grams of water. And then we're going to calculate the molar mass of water. It's 2 times 1.008 plus 16, which is 18.016. And then I need to convert to moles of hydrogen. How many moles of hydrogen in 1 mole of water? 2. Again, that just comes from the formula, H2O. So I've got 0.819 divided by 18.016 times 2. And again, 3 significant figures. The initial zeros don't count. 909, there's my 3 sig figs. Keep 2 extras. That's moles of hydrogen. Now we divide by the smallest. So we said, well, this is the smallest one. So I'm going to divide by that. And that's going to equal 1. So fine. We're going to take this one and divide by the smallest. Could somebody slide that door closed back there? Thank you. So this is coming out to be 2.5008. Can I round that to 2 or to 3? No. That's 2.5, right? If I multiply this by 2 times 2, I get 5.0017. Now that's plenty close to round to 5. So that's 5. I need the ratio 1 to 2.5. To stay the same ratio, I just want it to be whole numbers. So I multiplied this one by 2. I need to multiply this by 2. So a ratio of 1 to 2.5 is the same as a ratio of 2 to 5. Does that make sense? So I've got 2 carbons for every 5 hydrogens. And that's the empirical formula. Any questions? The combustion analysis problems just get a little tedious, right? And sometimes you're calculating stuff and you forget where you're going with that, right? You're like, wow, I did all these great calculations, but what does it mean? It's important to learn how to write stuff down so that you don't get lost. Let's do another one. Upon combustion, a 0.8009 gram sample of a compound containing only carbon, hydrogen, and oxygen produced 1.6004 grams of CO2 and 0.6551 grams of H2O. Find the empirical formula. So this one's a little bit different because we have carbon, hydrogen, and oxygen. So we can calculate the moles of carbon and hydrogen like we did in the last problem. So I'm going to do that kind of quickly here. That's not what I want. 1.604. Nope. There we go. With the CO2. We need to convert to moles of CO2. And I've done this so many times that I remember the mass of CO2. It's a little bit disturbing. And then there's 1 mole of carbon for every 1 mole of CO2. So I've got 1.6004 divided by 44.01. 0.0363, 5 sig figs this time. Oops, I'm having trouble copying numbers. 3634, there's my 5 sig figs, 44. Moles of carbon. And then I find moles of hydrogen from the mass of the water, 0.6551 grams of H2O, times 1 mole of H2O, divided by the molar mass, 18.016 grams of H2O. Again, that one's stuck in my head. And then we look at the formula, H2O, so there's 2 moles of hydrogen to 1 mole of water. .6551 divided by 18.016 times 2. Seven, 42 moles of hydrogen. Any questions? We're not done yet. This part is the same as the previous problem. And if the compound didn't have oxygen in it, we could just do a ratio and be done with it. But the compound also has oxygen in it, and we have to figure out how much oxygen does it have. We can't do it from the CO2 or from the H2O because the oxygens here most likely came from the oxygen that we stuck into the furnace to burn it. The 5th sig fig here would be the 4, but this number only had 4. Yeah. And again, sig figs on problems like this, we don't need to be exact on them. If you err on the side of too many, you'll be fine. If you round this off to 0.07, you'll probably be in trouble. So what we have to do to find the mass of the oxygen is we know the mass of the original sample. We need to subtract the mass of hydrogen and the mass of carbon. The difference is the mass of oxygen. So we have moles of carbon and we have moles of hydrogen. So we need to find the masses of these as well. So let me do it like this. So there's moles of carbon, and if I multiply by the mass of carbon, 12.01 grams per mole, that'll give me the mass of the carbon, right? So 0.0363644 times 12.01. So that's 0.436736, whatever. That's the mass of carbon. And then to find the mass of the hydrogen, we take the moles of hydrogen and multiply by the molar mass of hydrogen. Again, here hydrogen is not, we don't have to consider that it's a diatomic element here because it's not by itself. It's with carbon and oxygen. So the mass of the hydrogen is 0.07330. I'll just throw a couple extras in there. Everybody okay with that? I found the moles because I need those to do the empirical formula. But I also need to go one step farther and get the mass. So this is the mass of carbon. This is the mass of hydrogen. You can kind of look at that and see that those two added up do not equal 0.8009. The difference is the mass of the oxygen. So I'm just going to do this down in the corner here. 0.8009 grams of that substance minus 0.436736 grams of carbon minus 0.0733059 grams of hydrogen. Ah, 0.8009. I'm not feeling real confident about numbers I get off my cell phone calculator. Anybody else get that? Did I do it right? So, mass of compound minus the mass of carbon minus the mass of hydrogen, this must be the mass of the oxygen. So that's the mass of oxygen. Then we have to figure out how many moles of oxygen we have. So we've got 0.2908 64 grams of oxygen. And we just need to convert that to moles. 1 mole of oxygen is 16.00 grams. So we see that the grams, cancel out. So that number divided by 16. Did you get that? The last 4 digits were different. That would probably be okay. Doing sig figs here with this number, this would be the last significant digit right there. So, you agree or disagree with my math? You guys have calculators, right? You're not doing it with me? You made me do it all by myself. I feel so lonely and exposed up here. Yeah.
Or the 0.018, or not, no wait, no.
This one? Or this one?
Sorry,
What I like about my real calculators, I can see what I did.
The 0.29,
Uh-huh.
I got the last 3 digits, I got different, but the answer is the same.
Okay.
I don't know.
Let me just run that through again because I may have just put a number in wrong.
No, that's right. Yeah, just so the last 3 digits are a little bit different. Just say these should.
Okay, yeah, when I wrote it down, I think what I did here, I don't know what I did there. I'm not going to say I think I know what I did, but now I'm getting this.
Yeah, that's what I got.
Okay. So this is where knowing about sig figs is helpful because we recognize that the uncertain digit is here, and so, yeah, I did something wrong when I typed it in. Is it going to matter ultimately? No. If it was one of these digits, then it would be a problem. So this number is going to be good enough. So now we've got moles of oxygen, and we've got moles of carbon and moles of hydrogen.
So we
Divide them all by the smallest. So we look at that and we see that the moles of oxygen is the smallest. So we're going to divide by itself. I'm just going to write ditto down there because I'm tired of doing this. So that's going to give us 1. And so I need to divide all the other ones by that same number, 0.18179, recognizing that it's probably a little bit off, but it shouldn't matter ultimately. I may have to run back to my office and get my calculator because this is really annoying. My cell phone's arguing with me. 0.3644 divided by 0.018179 equals. Okay, this one comes out to 2.000 actually. And the second one, this one comes out to 4.000. So those are definitely close enough that we can round. We don't have to do any multiplying. So we've got a 1 here, and a 4, and a 2. Now, in terms of how do you write out the formula, what order, I would just go with the order that they're mentioned in here. Carbon, hydrogen, and oxygen. So carbon is going to have a subscript 2, hydrogen has a subscript 4, and oxygen has a subscript of 1 that we don't actually write. Any questions? Yes? This number, this guy down here?
Yeah.
So I got the mass of oxygen by taking the mass of the compound, subtracting the mass of carbon, and the mass of hydrogen. So we have to find that by difference. And that's one of the things that I think makes science fun, is that there's these missing pieces and you have to figure out how to find them. It's not just all handed to you. You have to figure out, well, how can I find out what that is, the thing that I can't actually measure? If I measure everything else, then I can calculate it. Any other questions?